Okay, we can start. We have the pleasure to have Carlos Egues from São Paulo University. He's going to talk about topological phenomena in ordinary systems. So please, thank you.
Thank you, Marina. So first of all, let me thank Marina on behalf of the organizers for the opportunity to be here. I'm going to talk about some topological phenomena. I use the word ordinary here because originally I intended to talk about some ordinary system, and I didn't want to use the M word, the Majorana word, so which is now ordinary in any way. So this is actually part of a longer talk that I talk about quantum oscillations. It's just like 1/3 of it, which I expanded. And it also involves a new direction that I'm going, which is involve qubits and silicon germanium. And also this part here, which is like a mundane Shubnikov-de-Haas oscillations. But also in in the most recent work here, it is also in topological systems. That's work done by my student and a former collaborator, Poliana Penteado. So there is a new development, which is on the archive. I'm going to focus basically on those two papers. So up front, I'm going to show you the main results, basically, and you may all know that, as I will tell you today a little bit, that this Majorana business is very controversial since the very beginning because of a zero bias peak that is not really fully understood in terms of what is really the smoking gun for it. And so we had come up in this work here with a way to, we claim, to probe it in a very specific way and which would overcome, in principle, difficulties that people had. So this is basically what it is. It's basically measuring the conductance on either side and comparing them. There's a correlation, a very strong correlation between the measured conductance, local conductances in these systems. So before I move on, because this is not the main focus of the works we've done and we've been doing over the last 10 years, and here's a piece of advice for the young graduate students. Majorana is not a good place for you to start right now if you want to have a career. So, of course, we had this paper, and this is the third paper we had in a period of 10 years. We have been involved in many different aspects of topological matter in mundane semiconductors, like, for instance, this one here is one of my favorite pieces of work, which involves this ordinary double well system with inter-subband spin-orbit coupling, and you can engineer it to have a band inversion. So it's an all-electron topological insulator, as opposed to the standard BHC model, which is a great model, which is more complicated because it involves valence and conduction electrons. I'm also going to be focusing on today on this one here, which involves the Kitaev coupled chain. And there's also this nice work, which involves also an ordinary system. It's basically, again, a two-dimensional electron gas, a indium arsenide, with two subbands. That's the novelty here. And for those of you who are familiar with the concept of a persistent spin helix, that's a spin texture. It's not a ground state property. It's basically an excitation that you can create in the system. It looks like this, a persistent spin helix. You can have two of them, actually, when you have a two-subband system. And you can have the system set up so that you have them perpendicular to each other. So when you add the density, you end up with a skyrmionic texture, which is topological. So that's the first example I know of in which you can have this kind of texture in a non-interacting system. So that's basically gallium arsenide or indium gallium arsenide, if you want. It has to be a semiconductor very stronger spin orbit coupling. Now this is also a nice concept, which in fact involves the usual persistent spin helix, which is something we studied some 20 plus years ago, in which you have two types of competing spin orbit interactions, the Dresselhaus, so-called Dresselhaus, and the Rajba, and they can compete. And there's a point, which some people would call the symmetry point, for which the coupling constants are equal and they sort of balance out, and the spin sort of becomes a good quantum number again. We generalized this, at that time, we thought that there was only one particular configuration in which alpha would be equals to beta. Alpha and beta are the coupling constants for the spin orbit interaction. It turns out that in this more recent work, in collaboration with the group of Dominic Tuzumul in Basel and also David Archulon in Chicago, we're able to show that it is possible to tune this constant as a function of the density over a wide range of densities so that they keep locked to each other. And because of that, this helix that you had at a particular value there, this alpha and beta, they actually define the pitch of the helix. So now you can actually tune the density and you can make this persistent spin helix expand. That's what is illustrated here. In principle, you can now have these things alpha and beta locked. And that's important for reducing the spin orbit, the detrimental part of the spin orbit interaction, which is spin flip and spin decoherence. So today is a plan I have. I'm going to show briefly some earlier work we had, and then I'll focus on these two more recent works that involves the Majoranas in Kitaev chains, and actually physical realizations of this Kitaev chain. What is not so visible here is what I plan to talk about. Then I gave up. It would be too much, but you can ask me later. I'm going to be here to the end of the week. So here's some of the our collaborators in recent years. But the work today I'm going to talk about is done by my former PhD student, Rodrigo, who just finished his PhD thesis, and also Poliana Penteado, who is a longtime collaborator. So back in 2012, for those of you who were at the March meeting in Boston, there was this big fuss. I felt like a deja vu, this year again at the March meeting when the Microsoft guys were presenting their results again, and the room was crowded just like back then. So I was there, and when I went back home, I gave a journal club discussing the paper, and it was about the Majorana. And that paper, by the way, was not retracted. It was still believed to be they use the word signatures for this, whatever signature is, I'm going to show you now. So that paper is fine, but the whole field at some point became very messy with a lot of retractions and so on. So for the non-expert, let me just, for the students mainly, a lot of interesting physics, despite the fact that this field is a bit of a mess at the moment, in my opinion. There are a lot of interesting physics, especially for to learn quantum mechanics at the undergraduate level. So I'm not going to go through all of that, but basically, what the Majoranas we are interested in are not really the ones that Majorana actually proposed, which is basically to find a solution, a real solution to the Dirac equation, as opposed to a complex solution. That means that the field is real, and hence it's a chargeless particle in this sense. Those Majoranas, so he asked this question back in the 30s, and of course the answer is yes. And those objects are chargeless, and their own antiparticles, so they have to be chargeless. It's not like the electron and positrons. But of course, these are not really the ones that are making the big, splash or trying to in the current literature, because they are basically ordinary fermions in the sense that they obey Fermi-Dirac statistics. The ones we are interested in are going to be the Majorana bound states. But even those, I think there's been a lot of activity in the elementary particle community to try to detect them. A lot of efforts. This is, an article in Physics back in 2018. I don't think the scenario changed. So, but one way to detect it would be through this the decay, the neutrinoless double beta decay. So right here, if they would be a no neutrino emitted, then this would be a Majorana. But I think that's still not quite there. It's probably not. Anyway, I'm going to go back to this. It's very familiar to all of you here, since for the last week and this week you've seen this similar version of this Hamiltonian here. So this describes a 1D superconductor that can p-type superconductor. That means that the pairing involves same spin, so it's spinless in this sense. This was proposed back, in fact, if you go back to as far back as 61 in this famous work of Lieb and Schutz and Wu, I think, you're going to find, I think, connections with, with this model because of the Jordan-Wigner transformation. But of course, it came to prominence because of the work of Kitaev back in 2001. So this, in bulk, if you use periodic boundary conditions, you can easily solve this by going to K-space, because it's translation invariant, and you can easily find the quasi-particle excitations there. So you can do that by finding a Bogolubov transformation that diagonalizes this problem. And at this point, I'm going to already use this slide to emphasize why, in principle, you would need to use superconductivity to search for this kind of Majoranas, right? So this is bulk, but still I'm going to cheat a little bit and say that, in principle, at k equals 0, this operator here, if I take the dagger of it, and then consider, say, the k equals 0 and u equals v, then you have a equals a dagger. That means that in the language of field theory, that would be a particle being equals to its antiparticle. Of course, that doesn't happen in bulk. That's what I'm saying. I'm just cheating here. But of course, in a finite system, which I'm going to show next, when this is finite or open boundary conditions, you can then introduce these Majoranas operators, right? And the first time I've heard about this was in this earlier paper, where they use the ideas of Majorana operators to tackle the Kondo lattice problem. So these operators are defined in terms of the ordinary fermionic operators of the Kitaev chain, like electrons operators here. It's like the real and imaginary part. So you can always define those two, and then by constructions, they obey this condition here, and they have this anti-commutation relation here. So I can invert this and write Cx and Cx dagger, and then I can rewrite the original Kitaev Hamiltonian in terms of the new operators. So this operator so far is just a mathematical transformation. It doesn't add anything new. You could solve, for instance, if you have free time in your hand, you can probably try to solve the hydrogen atom using Majorana operators, right? It's just a mathematical transformation. It's probably useless in that case, and probably very hard, never tried, though. But it turns out that for this problem, it has an advantage when you go for this Majorana chain. I just rewrote then the Kitaev original chain like that. And in each site, so A and B are just the two site Majoranas that I just introduced. And so in each site of the Kitaev chain, so there's site 1, site 2, site 3, we have two Majorana operators. That's how I defined it, right? So I can, so this term here is basically connecting, each pair. So A and B are on the same site. Then I can do the same thing for the second term, which basically couples Majorana B to Majorana A in different sites. And the last one is basically that kind of coupling, right? As you can see, AJ and BJ plus 1. That's what this does. So far, there's nothing new there. So let's now look at a simple case in which I'm going to throw away some of these terms. For instance, let's take what we were going to call the trivial phase for now. Assume mu is 0, some site energy if you want, and then I just take delta and T equals 0. Delta is, as I see in the previous slide, is just the pairing gap of the superconductor p-type, and T is just the hopping matrix element, the tight binding kind of matrix element, right? So I take all of them to 0. So everything goes away, and you're left with only that first term. And then, of course, you can, that's the usual fermion, right? You can go back to the, so that's the solution, right? The Hamiltonian is just like that. And I can go back to the usual fermion representation. This is the atomic limit of a tight binding chain, right? So it's electron cannot really hop anymore from one site to another. I'm having trouble here with the, so this is just what we call a trivial insulator, right? Localized electrons in each site. Now, let's look at the non-trivial phase, and that's where I think this procedure of going to this Majorana representation is useful for you to understand why, how this Majorana, whatever it is, will show up. So I'm going to take now the case where I choose the site energy or the chemical potential to be 0, and I take this point, particular configuration where delta is equal T. So I'm left with just this part here. And as you can see, by looking at this Hamiltonian, there is no gamma A1 and gamma Bn in the Hamiltonian. So those are, the two operators are not in Hamiltonian. Hence, they have 0 energy if you write the Hamiltonian in terms of this Bogoliubov-Dejean description that I'm going to show you later on. You can actually solve this very easily. And these two operators, they correspond now to 0 energy Majorana modes. And it turns out that they will, as I will show you later, they correspond to solutions of these particles, if you wish, that live at the end of the chains, right? So that's basically the simple argument. So from these two Majoranas, gamma A1 and gamma B1, I can go back to the ordinary representation, fermionic representation, and I can define what it's known in the literature as a non-local fermion. So F is just the usual fermionic operator that obeys Pauli principle, for instance. Of course, the rest of the chain, you still have other Majoranas. You can go back and rewrite in terms of ordinary fermions. But there's nothing really special here except for the fact that when I move away from this, everything is going to be coupled. But the fact that the system is topological, it means, supposedly, if this is robust enough physically, not just mathematically, these end states will survive. And there should be something living on the edges, right? So the most important part, I think, is the fact that once you define this non-local fermion, this system now has a bound state right in the middle of the superconducting gap. And this bound state is described by this fermionic, ordinary fermionic state, and it can be occupied or not with one fermion. So the ground state of the whole system now is degenerate. And this degeneracy is the most important thing in this system because it will lead to braiding and the possibility of non-abelian statistics when if you go into that direction. So that's the origin of all of that. So that came out of this toy model. And it turns out that this toy model can, in principle, be realized experimentally. I'm going to show you next one possible realization, but there are many, especially with this revival of this area, I suppose, over the last maybe 3 years with what they call this finite Kitaev chain starting for like 2, 3, and so on sites, right? So they call it poor man's Majoranas. So that's the second part of my talk that I'm going to mention briefly, this subject. So the early days, I'm going to go briefly on that. So that's what was shown at the March meeting. So it turns out that people realized in the early 2000s that if you would combine a nanowire with strong spin-orbit interaction, like say indium antimonide, indium arsenide, together with a proximity-induced superconductivity. So you put a layer of an ordinary superconductor on top of the wire, and because of proximity, Cooper pairs can tunnel back and forth, and it induces superconductivity on the wire. This together with the fact that you apply a magnetic field in the system, you polarize the electrons. So there's a nice paper showing this connection. It's the Nature Physics. I think the first author is Alicia, where you show that you can actually, with these 3 ingredients, and the point is that those are 3 ordinary ingredients. It's not a p-type superconductor, because p-type superconductors are a rarity in nature, so you have to emulate it. So that's what you do. You take an S-wave superconductor, like aluminum, for instance, and you put it on top of the wire, and the spin-orbit interaction in the wire. So the wire by itself is not superconductor, but because of the proximity effect, it turns out that you generate all kinds of pairings in the wire. Up, up, down, down, up, down, down, up. So you have triplet and singlet or S-wave superconductivity. So by applying a magnetic field, you can show that this is possible. And then they measured, and that's what's shown here, basically the conductance through the system. So this is a normal metal, and the wire is right here. The superconductor is on top of the wire. So when they measure that, they, as a function of some gate voltage here, applied to the system. In principle, for those of you who are familiar with superconductivity, this is basically the density of states that you're seeing of the superconductor. I mean, at that time, in this very first experiment, this was not really a hard gap material, because the conductance is basically the density of state of the system that you're measuring. But the most important feature here is that, as they saw this zero bias peak right in the middle of the gap. So the gap is roughly, you can see here how tiny the gaps are. Usually in this system, this has not changed to this day. So this is like 200 micron. So it's 0.2 milli electron volts. So it's tiny, and this goes. It's true for all this topological system, including topological insulators, and the so-called robustness due to topology is not quite like that when you have a real system, because this is all protected by a gap, and the gap is tiny. So once you close this gap, this goes away. So in any case, there's this peak there, and that was the big fuss. But and of course, we started very early on already. And a year later, we managed to work on this. And then from day one, people start challenging this interpretation of this zero bias peak as due to the Majorana. I just told you from the previous slide that because the Kitaev chain has a bound state right in the middle of the gap. That's the origin of the zero mode, because as you drive the system with the current, because now you have this mode right in the middle of the gap, there's a peak there. So that's basically the interpretation. As it turns out, that there are a lot of works showing that, well, it's not quite like that. It could be many things. It could be disorder. It could be the Kondo effect. It could be Andreev, whatever. So many papers that it's not even fun. I even have one paper together with Wei Chen, who is here, on that, which is right here. As you can see in the trivial for this, so it's a Kitaev chain in a normal metal, and if you plot the density of state, you see peaks right in the middle, and this is both in the trivial and non-trivial phases, so cannot really tell whether it's a Majorana mode or not. But at some point, I think that got me to thinking that I think it's a personal opinion, as opposed to just try to show again. Because as I mentioned, let me go back one slide here. At the very beginning, or maybe later there's another reference. At the very beginning, there was already a paper by Marcel Franz from UBC, University of British Columbia, I think, where he already outlined, it's a long paper where, pointing out all the problems with the zero bias peak. But people kept over the next 10 years until to this day is trying to show, oh, it's fake, it's fake, it's fake, it's a fake mode. So we tried to actually, let's find a solution. So back then, and I think this is a very nice paper we have where we proposed, you take the Kitaev chain, you couple it to a dot, and you drive a current through here. It's a two-terminal measurement, not along the chain, and in the original paper there's no dot, so this is a new geometry. And then, of course, this has the advantage that oops, it went away. So what we found when you measure this current here, we saw this plateau here. So there are many parameters here, it doesn't matter, but this is a configuration in which the system is topological. So what happens is that even when the dot level is far above the Fermi energy of the leads, so in principle, if there's the dot is in the middle and there's no level that is resonance, so the level is up here, there's no current. But when we have a Majorana chain, what happens, and then we show in this work, is that the Majoranas in the topological regime that should appear in the last site of this chain here, it actually leaks into the dot, and it generates a resonance. Even though the dot level is up there, it generates a resonance right at the Fermi level. So this resonance here leads to a conductance, which gives you a 1/2 E squared over H. It's a plateau, actually, quite robust plateau there. And the important thing here is that, at least in this case, we could rule out the Kondo effect explanation for the zero bias peak. Because in this case, in particular, when the energy of the dot is up here, the dot is empty, so there's no Kondo effect, right? So, the Kondo effect is this many-body, effect where if you have at least the mesoscopic Kondo effect of a dot with a spin that can spin flip, it's degenerate. And then, of course, because the coupling to the leads you have with an anti-ferromagnetic coupling, there's what they call a Kondo cloud that screens this impurity or the spin of the electron in the dot, and that generates a very sharp resonance right at the Fermi surface or at the Fermi energy of the leads, and that could give you a peak, right? So in this case, we claim we would rule out at least the Kondo effect. But back then, and revisiting this paper recently, we saw that even back then we never used this word fake zero modes, but it shows here that the conductance through the system, you can actually mimic the topological regime, or you have a plateau here, say, as a function of the chemical potential of the Kitaev chain, with the dot, even when there's no superconductivity. So you can see here, this is flat, just like here. The difference is that this is not robust when you change the parameters of the system. Then the peak the peak in the conductance moves away from this, as opposed to the topological regime. When I change, say T0 here, is just the coupling of the last site of the chain to the dot. So as I vary this, if I have a Majorana in the dot, the conductance remains constant, as opposed to the trivial case. So that's one way to tell apart whether this system is topological or not. We also studied this in collaboration with a colleague from the University of São Paulo here in São Paulo capital, and a postdoc at that time. We included the Kondo effect as well, if it's ever going to come up. So, too late. So what happens is when you have a Kondo, so we used, or they used, I'm not a DMRG person, but we did the spin-full model beyond the Kitaev. So we have a spinless, so we have a dot now that can be up and down, and we included the Kondo effect. So the Kondo effect, if there's no Majorana, you should see a peak at 2 E²/h. So because of the Majorana, the Majorana sort of eats away 1/2 of E²/h. That's why you go from, say, 3/2 right here, where you have the Majorana, and the Kondo. Instead of 2, you have 1.5. But then when you kill the Kondo, imagine you apply some magnetic field and you kill the Kondo effect, it goes back to the 1/2 that we had previously. So this is showing that indeed there's this interplay between the Majorana and Kondo physics in the system. So then people started thinking about next generations of devices, and to use fancier approaches where you would calculate, say, the non-local conductance, meaning the left to right conductance in the system. And they came up with 3 terminal devices that culminated with the so-called Microsoft quantum protocol, or topological gap protocol, they call it. It was published in 2023. There was a big fuss, and then recently they also used the same kind of protocol. A protocol is a set of measurements in principle that you do, and you correlate them to tell you whether or not you have a Majorana. You observe, what you observe as a peak is a Majorana, and they find a tiny region in parameter space where, in principle, there is a Majorana. So we then. Okay, of course, this is very controversial. I didn't even bother to update this slide because there are more. There are more now comments and replies, especially after the publication of the Nature paper earlier this year with the Majorana 1. So you can now buy a chip. Well, I don't know if you can buy it, but it exists. I'm going to show you a picture of it. It's not topological, though, in principle. So there's a lot of back and forth and retractions and, blogs with, people spending a lot of their time, and I really would not advise young students to be wasting their times, trying to prove that someone is wrong, because it's not a good way to be famous. You rather become infamous. So we took this as a motivation to study the very same device. And of course, there are a lot of criticisms about this Microsoft device, which was published in PRB, and not all the data was released, and the details, it cannot really, if you want to do exactly what they did, it's not possible. But we didn't care too much. We just considered this device, which is basically exactly the same device, same material, same parameters. We're doing basically the same thing, to the extent that we can do the same thing, because they have an army of engineers and quantum engineers and people doing simulation with all kinds of disorders. We don't do that, of course, but that's what we claim is that the principle is more general than that. It's not about the details. So it's exactly the same system, which realizes a Kitaev chain, meaning you have the same ingredients that I told you before, a nanowire with spin orbit, with proximity-induced superconductivity, and a Zeeman field. They're all here. Don't bother to read all that. And then, of course, there's the coupling to the leads, right? And, and the coupling to the leads are like this, like normal metals, left and right. And the coupling to the leads is just this here. Like the last site here in this discretized version of Hamiltonian is coupled to the left and coupled to the right. What is new then? What is new is that we now will consider, and the results I'm going to show you is all related to varying one of the barriers, the tunnel barriers here. So every device calculation that there's in the literature, with the exception of one particular system, particular paper, they all consider symmetric devices. So, and this is very easy. You can easily vary these barriers here. And that's what they did. So we basically will calculate the conductance through, from left to the superconductor, and then from the right to the superconductor. We can also calculate from left to right, but we didn't want to do that because that's the Microsoft protocol. They calculate the full thing. And so we're going to do that. We use Landauer-Buetiker approach with Green's function. And of course, superconductivity is well suited when it's grounded because it has a well-defined chemical potential for you to use the Landauer-Buetiker approach, which is a formulation of it's basically scattering theory, ordinary quantum mechanics for a non-interacting system. And of course, the superconductor is a non-interacting system in mean field theory, the Boole-Lejeune transformation. So in principle, we can calculate the conductance matrix, basically taking the derivative of that in the limit of small voltage applied. And in this regime, the conductance alpha here is just the lead left or right. So L and I, that's what we are interested in mostly. And then here we have many processes that contribute to this, because this, as opposed to the ordinary scattering problems that we all solve in ordinary quantum mechanics when you send an electron through a barrier or a double barrier that you have resonant tunneling and so on. Here we have a superconductor, so in principle you can send an electron in, and of course, because of a gap, it cannot go through, because it's right at the middle of the gap. But there are other processes that can happen. One of them illustrated here is that this impinging electron can hold hands with another electron here, create a Cooper pair, and hop into the superconductor, and a hole is reflected back. That's the one example of what we call an Andreev process. Now, illustrated here is just the normal superconductor junction. Here we have a normal superconductor and another normal, right? So in principle, we have different processes like that, in which the one I just described here is one example of what we call LAR, local Andreev reflection. There is also CAR, cross Andreev reflection. This is the same process, similar process in which an electron is impinging from this side, and then there's another normal one here. And then what happens is another electron from the other side hold hands with it and hop into the superconductor, and the hole is going out to the other side. That's cross Andreev process. And there's also the ordinary direct tunneling, where an electron goes through the system. And that's the ordinary quantum mechanical ones. It turns out that the parameter range that we have, the local Andreev process, this one exemplified here, is the most important one for us. And the amplitudes, we calculate all these amplitudes, and it turns out, I didn't mention that before, but there is a critical value of the Zeeman field in this system, for which this nanowire with the superconductor, with the spin orbit, in which it becomes a topological system. It becomes a Kitaev model. It can be mapped into the Kitaev model. So that's VZ here. VZ equals VC1 here means that I tune the magnetic field, which is VZ, and before the Kitaev chain or this nanowire is non-topological, all these Andreev processes are very tiny. They're not zero. They're zero in this scale, but they're very tiny. And once you create, once the system becomes topological and there appears a Majorana mode in the system, then there's a jump in this probability here for all these processes, and the green is the total one, and that's how. So there's this jump. This jump signals a phase transition, and I'm going to show you results when I'm in either side of this for the conductance. This transmission here, the alpha beta, in some cases it can be, they're both equal sometimes, but very small, and they're proportional to what we call the hybridization energy. That's a very important quantity in this Majorana system, because I showed you in the first slide that when you have the Majorana end modes in this T equal delta, very particular point, they're completely decoupled. But it turns out that when delta is not exactly equal, you have the whole chain in the middle coupling them, and that generates a coupling in and this hybridization, and they will split and not become a Majorana anymore. So strictly speaking, a Majorana only happens, and it's only a Majorana at zero energy. So if you move slightly away from it, it immediately becomes a, we call it the topological Andreev bound state. So it can be still useful, but strictly speaking, it's not a Majorana framework. So that's the solution of the Schrödinger equation for this system without the leads, just the Bogolubov de Gennes. And as you can see, I'm plotting the wave function. I mean, here's the wave function of the non-local fermion, right? So you can imagine each half of this being one of the Majoranas I mentioned to you before, right? So gamma A1 and gamma Bn. So half of this is one Majorana. So two Majoranas form one non-local fermion. And of course, this is a function of the magnetic field. Before this Vc, and this is the criteria that people have derived in bulk for which, for when a Majorana would appear. So right at 1, the gap sort of closes, if you wish. I don't really like using these words because it's a finite system. In principle, gap is defined for the bulk, but still people use this nomenclature here. So the gap sort of closes, and then from then on you have something that looks like a zero mode, but in fact, if you zoom in, it actually oscillates. And that oscillation is important because it can be measured in principle. So we're going to use this again. But now, since I'm probably going to be run out of time, I'm going to show you what is the result, the most important result that we claim is important to set up a protocol or to complement any kind of protocol to tell apart Majorana bound states from ordinary zero modes that could be due to whatever. So as I mentioned to you, what is new in this system or in this model is the fact that we're going to be varying the barriers, say the left one, the right one, it doesn't matter. It's the ratio that matters here. And then I'm going to plot here GLL, which is the conductance. Conductance for the students is just like 1 over R if you want. Ohm's law, V equals Ri, E equals I equals GV. So it's linear response. So it's the coefficient connecting current to the voltage. So as you can see here, I'm going to tune the system, say, for the trivial case, I plot this and I vary this ratio here. So I take measurements. And what happens is that you can see, I'm going to go back again so you can see, look at the dot on the left and the right. So on the left, it's just straight. So the conductance doesn't really change in the trivial case, which makes sense, right? Because there's nothing in the middle. So if I vary the potential on one side, nothing happens on the other side. So the conductance on this side here doesn't really know what's happening on the other side in the trivial case, right? Now, so they are uncorrelated, right? And I emphasize this kind of measurement, the plots have never been, done in the literature, the measurements, and it would be interesting to see it. So in the topological case now, so I tune the system parameters so that there's a Majorana supposedly in my model, and I do the same thing again. I vary, and you can see that now the two conductances are correlated. So there is a bunch of lines here. I can discuss this. Basically, different lines along within this topological phase. But the essence here is that the system, for the topological case, if you just measure the two conductances, they will be correlated as opposed to the other one, right? How much time do I have, please? 15? 15, okay, good. So here again, just a quick explanation of what we we just saw. And you know, we can see, so this is again the amplitudes of the total LAR and refraction probabilities, as I showed you before. And here I have more curves for all the processes, right? So I can come in with spin up, and then go back with spin down the hole, but I can also have processes that involve same spin. This is because now our superconductor is a p-type, and you have a Majorana mode in the middle, and the enhancement here is really because now I have a zero mode right sitting right in the middle. So there's all these processes, but the dominant one, as you can see here, is basically, you know, for instance, the same spin here, right at the beginning. And so on the right here, B here, I'm plotting these amplitudes as a function of the barrier. And as you can see, they all go down, right? And that's basically why the conductance is going down, because the conductance is proportional to the end-wave state. I can also explain this in terms of the density of states. If I have time, I'm going to go through this. So it's well understood, this kind of decay, and you can have a protocol for that. So yeah, the density of states is right here. It turns out that it's possible we calculate this using Green's function, basically define through this retarded Green's function. You stick in the Bogoliubov-Dejean Hamiltonian that we have, and you calculate the density of state as the imaginary part. It turns out that the local density of states of the system, which is basically the conductance, as we go from the symmetric configuration, where the density of state right at zero energy, so zero is right there, right? So the middle point here is zero, right? As you go from the symmetric configuration is nu, which is the asymmetry parameter, where it's zero, to the case where it's very asymmetric, this density of state, the local density of state, develop this dip here. It's not a gap, we're just using quotes here. But there's you lose some spectral power right here. So that's another way. So there's a dip, if you want, in this conductance here. And this is due to the fact that, you know, because of that, basically, right? So the dip you're seeing here on GLL is basically because of that. That's another way to see it. And what's plotted here, in this case, is just the local density of states. You know, it sort of starts piling up here as the barrier increases, right? So in this case, you get the dip there. We can also derive, you know, we did this very carefully. This is a long paper that I mentioned before. You see the reference later on. We can also have analytical results. We did an effective model, considering just a dot with a single Majorana mode, forgetting about, you know, the rest of the spectrum. And for that, you can calculate all these amplitudes. And there's an interesting thing you can see here. The ordinary, the tunneling, and the cross and wave reflection, they're both proportional to the hybridization energy is squared. So that's why it's actually tiny compared to the local and wave reflection. So this hybridization energy, as I said, it's controlled by the size of the system. If you have a very long chain, you know, ideally, a zero mode only exists for an infinite chain, because then there's no talk between the two Majoranas. But of course, the finite system is what we have. And but this can be small enough that you can, for the systems we study, we're using the same parameters as the Microsoft, to the extent that we can figure out what the parameters are there. This is basically dominated, GLL is basically dominated by the local and wave reflection. And we call this, in the fact that both conductance on the left and right side, that they are correlated and they go down like that. We call this the non-locality of the local and wave reflection, because it's something that happens on one side of the system. It's affecting the conductance on the other side via this epsilon m. So epsilon m is important in the system. It's very small, but this is what's conveying the information, right? So this non-locality that we talk about here, has nothing to do with the non-local fermion. And this, so there are some papers trying to use this non-local fermion that I derived, that I showed you before, as a means of teleporting, states from one side to another. I think there are criticisms of that. I'm not sure if it's not into this business, but it's not. It has nothing to do with that. The non-locality here is a very mundane, description of doing something on one side and something happening on the other side of the system. Of course, the referee gave a hard time. Yes, 10 minutes. And we had to include temperature. So this was a long process we include because everything we presented so far, and that's one reason I tell you guys, the young guys, if you want to publish your nice PRL when you're young, it's not a good idea to work on Majoranas because now they want you to be God and do everything, right? We actually have a pretty long paper with everything already, I'm not even mentioning the disorder, we have it all there. But then they want more, and of course, it's like publishing a paper on the Kondo effect these days, right? Who would do that? Yeah, so it's impossible. But we did do a good job. We, introduced the temperature effect, and it survives because the question is, oh, does it survive? Yeah, it does survive. For instance, the dots here. So look at this one here, up to say 20 millikelvin. For 10 millikelvin, that's the red dot here, and you have the same thing here, red dot there. So there is a correlation. I mean, the solid curves are the ones I just showed you before, right? So they are correlated in the topological regime. But of course, if you go up to like 30, 40 millikelvin, then say this one here, the square dot, then it's not really correlated anymore, right? I mean, one goes down faster. And that has to do with the KBT, the energy scales relevant here are KBT, and this hybridization energy. So, this protocol for us would work whenever this hybridization energy is larger than KBT. It's a very straightforward explanation, and you can ask me later. It's basically the Fermi function that appears there. There's a window in which you're basically sampling around epsilon, zero energy. So if KBT is larger, you start sampling the whole density of state, and then you lose this correlation. Anyway, in the process, we discovered something else, and then we added in the paper because we went back and looked at these oscillations here. As I mentioned to you before, right? I mean, if you zoom in, there are actually oscillations, and I'm just gonna. Yeah, so and of course at that time I would make jokes about our election. There were some kind of oscillations there. Fortunately, it didn't go back, right? And let's hope we will not see oscillations in our next election. And this oscillation has to do with the Majorana hybridization energy. So we calculated, and I mean that's gonna go faster here. But basically, if we include temperature effects and define this new quantity here, which we call, it's basically this asymmetric conductance deviation, right? So it's basically the conductance measured on just one side, on the left side, because we already here, since the temperature can be very high here for this part of the talk, can go up to 150 Kelvin. This is very realistic, You can still find this non-local effect in this fluctuation here. And it actually, you see oscillations now on this quantity that maps exactly the oscillations on this black curve here is basically the hybridization energy, the oscillation, the amount of oscillation, you see that. Now, you can, this calculation shows that these fluctuations, right? If you take, say, I mean, it's a very asymmetric, say, I think for this case here, U is like 30, if I'm not mistaken. So we're around here, and then you plot it as a function of the magnetic field. And so this quantity maps out the Majorana oscillation. So, and this, as opposed to the previous case, it can be measured at a much higher temperature. This survives completely. So this is the part where I make a joke. I gave this talk, in Iowa, and for some of you, the older, guys, and girls will probably remember this movie. If you're born before, many of you were born after '89. This is an '89 movie, and it's about, it's called Field of Dreams, right? So you had to build the field. There's this farm. This is Iowa. That was, I was in Iowa, so I had to make a joke there. Visiting my former student, the collaborator, another collaborator, Michael Flate, who were both profs there. So in this Field of Dreams movie, this is Kevin Costner. He had to build a field so that some ghosts would come and solve some issues of the past. It has to do with the Chicago Sox, the baseball team, right? So the Mariana Field is like a Field of Dreams, and then I'm not going to make a comment about being, you take a pick. It can be a Field of Dreams pejoratively or not. I tend to view it as a Field of Dreams. It could be very interesting. And the thing about the movie is that you had to build. There was this ghost in this cornfield that would come to the guy and say, and whisper, build. If you build it, he will come. That would be like the ghost that would come and solve something, right? So, and I think here it's kind of like that in the following sense. Some of the theories, right, that are used here. So this is a composite Torre Mariana generated. I really had a long discussion with the ChatGPT, really giving it a hard time because I wanted the picture of Mariana with Mariana's face, and that's the paid version, by the way. And it failed miserably. So I would have gave him a hard time. And I said, well, at least take the cap. Let's see if you can have at least the hair. And then it failed miserably. It could not even make the same face there. But the reason I'm showing you this is that to criticize some of the theories that I used to interpreting the data. Because it's like mean field theory. I remember when I was a graduate school, I had a very good many-body physics teacher. It was Professor Daniel Cox, who is also a well-known guy in the condo business. And he would tell us, when teaching, mean field theory, you have to build something, your order parameter. So if you want to find a solution in mean field that has a helical in ferromagnetism, for instance, you have to be able to guess good, the correct symmetry of the order parameter. The same with BCS, and you can get the Nobel Prize in this case, right? So you guess that you can pair C dagger with C dagger, and then you get your solution. So I think some of the theories that I use, they're biased models to that you put Majorana in and you interpret it as a Majorana, so you see Majoranas. Anyway, just briefly, this is the new paper that came out, I think, February 2025. It's a nice exercise for you to not only read the paper, but also go through the referee reports. I strongly advise the students to do that. So there's a Majorana one now. There's a lot of caveats in the, of course, they had a press release with videos. I mean, if you're not an insider, you would believe, things are really, interesting. There's a lot of money and there's a lot of investors as well. And I'm not going to mention any, not making any bad cracks here since we're being recorded. But you can check some of these posts. This is actually in the Nature webpage. You can find this portfolio. And then there are all the referees there. And they I think, it's a nice exercise for the students to see how the system works. I'm pretty much involved in this for many years with the APS and being editorial board of the PRB and other things. So it's a different approach, I guess, when you're reviewing, we're being reviewed in high-profile journals. So I strongly encourage you to go through this, so the referee reports. I think one of the guys actually made the mistake of, coming out and saying who he was, and it turns out that apparently there's some issues with, correlations with authors. Philip Paul also wrote something about this. This is emphasized by many of the referees. This paper is not about a topological qubit. That has never been shown in the paper. It's about the geometry. The geometry is supposed to be very interesting, apparently, in this interferometric. They have, for when you have 4 Majoranas, then it's going to be easier to braid them to this geometry. That's what it's emphasized there. And there are a lot of criticism along the way in the reports about the language, all the fluff, all this, hype. And I have a deja vu now with this, just like in, 2012, when there was all this mass, that's all these nice things, and then, as we saw how it evolved. So I think people should learn from the mistakes in the past. So that's a comment by Chetan Nayak, and it says, of course, there's now new evidence, because it took them a year to publish this paper. Of course, now they claim, and I've seen, I was at the March meeting, I went to his talk, they actually measured other types of the Z and X gates, and that's supposed to show that the thing is topological. I have to say, you look at the data, people were not convinced. One of them, I think the X gate was fine, but the Z was fine, but the X gate was like just noise, right? So it was not really convincing. But I strongly encourage you to have a look at that. In 1 more minute, I will just go through this very quickly, because this is the last part that I want to emphasize. I think that's the fun part. So you go through this. That's the usual way to write Hamiltonian, like the Kitaev model in the Bogolubov-Dejean formalism. You just use a redundant basis and then it's just a huge matrix. You diagonalize it, basically, right? And to do that, of course, you can always diagonalize. That's the importance of that, right? Once you have it in this form, it's very easy to diagonalize the whole matrix, because you can diagonalize the Bogolubov-Dejean Hamiltonian, which is this one here, single particle, and then you construct a U operator, a unitary matrix. It's just the columns are just the eigenvectors of the Bogolubov-Dejean, and then you end up with a diagonal form of your Hamiltonian. In the process, you introduce the Bogolubov transformation, which, if you square, it's given by that. This is a fermionic operator in real space, if you want, because that's a lattice here. Now, the important part is that you can use this gamma square here to tell apart, or at least theoretically, whether you have a Majorana fermion or whether you have an ordinary fermion. And that's a very important thing that is not appreciated by many people, especially students that are at the beginning. A Majorana fermion is not an ordinary fermion, because gamma square is 1/2 or 1, depending on how you define. And if it's an ordinary fermion like a Bogolubov, the usual quasi-particle in superconductors, they are ordinary fermions. Have Pauli principle, like C dagger square is 0, or C square is also 0. So you can create and destroy, you can have a Fock space for ordinary fermions, but not for Majorana bound states. Now, the question is, can we relate this quantity here to an observable and then measure it? Well, I guess that's what I'm showing you here. You can calculate this, and we can, and we're really happy with this result, because we can correlate this gamma square here. So we're plotting gamma square as a function of T over delta, which is the parameters of the Kitaev chain, and are related to experiments, especially the new experiments that people have with finite Kitaev chains. And you can see that the conductance through the dot now I'm back to the old problem, right? It actually maps the 1/2 here, this plateau we have. It says, this plot says that right on the plateau, gamma square is actually 1 or 1/2, right? So it is really showing that through a conductance measurement, you're actually probing the nature of your fermionic state. So I think this is a very interesting result that in principle could be probed. I think we need more time, because people are now producing this artificial Kitaev chain, finite chains. They have like 2, 3, 4. Slowly they're growing, and in this paper here, this one here, we're studying this kind of, so we have like 9 here, and then 9 in this region here. That's where the system is topological. Anyway, I ran out of time, so I'm just going to end showing this slide with our conclusions, and I'm glad to take any questions. Thank you so much. Yeah, I think you should use, yeah, I would, we have a very important device here because, yeah.
So thank you, Egues, for the very nice talk. I'm curious about the thing you said about the non-locality in the correlations when you were looking at the conductance. And then you mentioned there was a discussion whether that was a kind of entanglement, I suppose, or not.
Yeah, well, what I mentioned is that, okay, maybe I can now show it here. It's already here. So this one, right? So what we call non-locality has nothing to do with the non-locality that people talk about when they're talking about teleportation and things like that. Non-locality here is just being used as a very mundane word to refer to the case that we have a gate on this side that we vary the barrier, and the conductance on this side feels that. So that's the only thing I mentioned. But there are papers, and I can give you the references, in which people try to use the non-local fermion. Remember the plot that I showed you where there's the wave function looks like that. So that's a very special fermion, right? Because it has as amplitude on one side and the other. You could tell me, well, that's not really special because a double barrier, a double well system is also like that, right? So I have a double well, the wave function is like that, and I have two, this and the anti-symmetric one, the asymmetric one. That's the big difference. That's the problem exactly. Here, when we talk about the local fermion, there's only one state, right? In the double well, you have a symmetric wave function and anti-symmetric wave function. So the minute you try to, say, inject an electron on this side, it immediately, if the system is far apart, it immediately hybridizes and it just localizes on this side. It doesn't go to the other side. But the hope is that with this kind of non-local fermion that we have here, because there's only one of them, this one here, in principle, you could inject something on this side, and I don't know, immediately you would find something on the other side. I'm not an expert on that, and I doubt this would, it's probably a very delicate configuration, but, I just want to emphasize that it's very different than the case that you have with the double well. So thank you.
Okay, more questions?
I'm going to make you use the microphone. I was waiting for my talk just for that. Because I was sitting in the back. I was sitting here and I had neck pain. I had to move back, but then it was over.
I wanted to ask whether you have some analytic understanding of this relationship between gamma squared and the conductance.
Okay. Here. Yeah. So gamma square, as I just defined, is basically the square of the Bogoliubov transformation in real space, right? It's a tight binding. There's no leads here. So this is just the Hamiltonian. Now, the conductance, of course, I have to couple it to the leads, right? And then I calculate. The conductance is just the same as I calculated before. Now, what we found numerically, unfortunately, I've been pushing my collaborators and my students to try to come up with an analytical. We haven't done that so far. But you can see that if you plot, so we call it non-abelian here just to say it doesn't mean it's just a different fermion, right? So that depends on the number of sites. So if this goes to infinity, then of course this would be a huge, there would be an infinite plateau, right? But as you can see here, the conductance for say 50 or 25, the size of the plateau coincides, with gamma square. Gamma square is also this plateau. It's the dotted line here for the blue one with 25 sites. And for 50, it's the green one. So right on top, when you measure 1/2 E square over H, which is what we proposed 10 years ago, there's no way you can say is this a Majorana? We thought, this is a Majorana. It leaked into the dot. But now we have further evidence that if you calculate this gamma square for this particular configuration, it actually is 1. So it should be a Majorana. We hope. We'll see whether they can measure that.
Okay, more questions? Okay, we thank again Jose.
Thank you.
Thank you.